Hello students, in the last class we have studied one corollary based on the theorem number 11, and in that corollary we have proved that if functions f1 and f2 are integrable on the closed interval a to b, then their product f1 f2 is also integrable on the closed interval a to b. Now we are going to define the Riemann sum, then we are going to define the integrability of a function in terms of the Riemann sum, and then we will solve some examples based on the Riemann sum. After that, we will also study some applications of this definition of integrability in terms of the Riemann sum. So, let us begin with the definition of the Riemann sum. Definition of the Riemann sum is: consider a partition P which consists of the points A, that is equal to x0, x1, x2, continued, xi minus 1, xi, and continued up to the xn which is equal to b of the closed interval a to b. And corresponding to this partition, we choose points t1, t2, continued up to the tn, such that xi minus 1 is less than equal to ti is less than equal to xi for I equal to 1 to n. How we are choosing the points? We are choosing the points ti such that ti is arbitrary point in the ith subinterval. Okay, ti is the arbitrary point in the ith subinterval. Means t1 belongs to the delta x1. t1 is any point which lies between x0 to x1. t2 is any point which lies between x1 to x2. t3 is any point which lies between x2 to x3, and so on. ti is any point which lies between xi minus 1 to xi. In this ways, we can choose the points ti for I equal to 1 to n. Then we consider the sum. The sum is given as SPF. SPF. Here S stands for the sum. P means for the partition P and F for the function F. So SPF, and this SPF we will call the Riemann sum of function f over the partition P. So we define the Riemann sum over the partition P for the function f equal to the summation over I equal to 1 to n f of ti into delta xi. This is a very important definition. Okay, so this is the definition of the Riemann sum. This is very important definition. So we consider the sum SPF, which is equal to the summation over I equal to 1 to n f of ti into delta xi. Okay, then this sum SPF is called the Riemann sum of function f over closed interval a to b relative to the partition P. Next, here ti are arbitrary, means we can choose ti as any one point which lies in the ith subinterval. So, as ti are arbitrary, therefore we may get infinitely many number of Riemann sums. Okay, so here ti are arbitrary and it can be any point in the ith subinterval, that is in delta xi. Next one, we say that the Riemann sum means SPF converges to the real number a as mu of p tends to 0. Mu of p means norm of the partition tends to 0 if for every epsilon greater than 0 there exists a delta greater than 0, such that the difference of Riemann sum over the partition P of for the function f minus a, this difference is less than epsilon for every partition of closed interval a to b with its norm mu of p less than delta. Here we say that the Riemann sum means SPF converges to a real number a as mu of p tends to 0, as norm of the partition tends to 0 if for every epsilon greater than 0 there exists a delta greater than 0, such that the difference of SPF means the Riemann sum and that real number a is less than epsilon for every partition P of closed interval a to b with its norm mu of p less than delta. And for every choice of points ti in delta xi, here ti can be any point in the delta xi interval. Next, if SPF means the Riemann sum converges to the a, if the Riemann sum of function f over the partition P converges to the real number A as norm of the partition tends to 0, then we write it as limit of the SPF as n tends to infinity is equal to A. Obviously, as norm of the partition tends to 0, then n will tend to infinity. N means the number of subintervals in the partition P. So definitely, as the norm of the partition tends to 0, then n will tend to infinity. Now next is the second definition of integrability. So definition is, a function f is said to be integrable on the closed interval a to b if limit of Riemann sum over the partition P for the function f exists as norm of the partition tends to 0, and then limit of the Riemann sum as norm of the partition tends to 0 is equal to the integration a to b f dx. This is the second definition of integrability. We have already studied the first definition of integrability at the beginning, which was as such that we have said that a bounded function f is said to be integrable on the closed interval a to b if the lower integral a to b f dx is equal to the upper integral a to b f dx. That was the first definition of integrability of a bounded function. Now, the second definition of integrability of bounded function just now we are defined, and it is, a function f is said to be integrable on the closed interval a to b if limit of the Riemann sum over the partition P of the function f exists as norm of the partition tends to 0, and then that limit is called the integration of function f from a to b. Okay, so like such is the second definition of integrability. Now next, both the definitions of integrability are equivalent, so this will mention as a remark. So remark is, both definitions of integrability are equivalent. Now next, some examples will solve by using this definition of integrability. So first example is, show that integration a to b f dx is equal to 11 by 2, where f of x equal to 3x plus 1. This is that example. If you remember, we have solved this example as a first example in the beginning of this unit number first, and at that time we have solved that example by using the first definition of integrability, which was lower integral equal to upper integral, then the function is integrable. Now we will solve the same example, but now we will use the second definition of integrability for solving this example. So let us proceed to the solution of this example. So solution is, let f of x is equal to 3x plus 1. Here the function which is to be integrated is the 3x plus 1. So we have denoted it by the f of x. The function f is bounded on the closed interval 1 to 2. It is clear that this function f of x equal to 3x plus 1 is bounded on the closed interval 1 to 2. That can be very easily checked. Okay. So since it is a linear function and the interval is finite, therefore it is a bounded function on the closed interval 1 to 2. Next, let us consider a partition of the closed interval 1 to 2 consisting of n plus 1 points, which means that we will get the n subintervals. Let P, which is equal to the set consisting of the points x0, which is equal to a, which is equal to the left end point means 1, comma x1, comma x2, comma continued up to xn, which is equal to the right end point of the interval, that is 2. Let P, which is this set, be a partition of closed interval 1 to 2 consisting of n plus 1 equidistant points. Okay, here we are considering the equidistant points in this partition. As if we consider the equidistant points, then it will be convenient for the solving this example. So therefore we are considering the equidistant point. So then this partition P divides closed interval 1 to 2 in n subintervals, and as the points are equidistant, therefore length of each subinterval will be equal, and length of each subinterval is, length of the interval will denote by the delta xi. So length of each subinterval is delta xi, and as each subinterval is of the equal length and there are n points in n subintervals in all, therefore the length of the each subinterval, that is delta xi, will be equal to right endpoint minus left endpoint divided by the number of subintervals, means that is equal to b minus a upon n. Okay, b minus a upon n. But this is equal to the 1 by n. Why it is so? Because b is equal to 2 and a is equal to 1. So therefore we got this as the 1 by n. Okay, so b minus a by n, which means that this is a 2 minus 1 by n, and 2 minus 1 by n is nothing but it is equal to the simply 1 by n. So therefore here we get delta xi is equal to 1 by n. Now next, now let us consider xi is equal to the 1 plus I by n. Okay, xi will be equal to 1 plus I by n, I equal to 1, 2 up to n, which means that x0 we have the, I will mention here for your understanding purpose, we have x0 equal to 1. Okay, the first point in the partition was the x0, which was equal to the left end point, that is 1. Then x1 was the second point in the partition, and x1 we are considering 1 plus I by n, and I, if we put I equal to 1, then this becomes 1 plus 1 by n. So x1 will be the 1 plus 1 by n. Okay, then x2 means in this formula for the xi we have to put I equal to 2, so we'll get 1 plus 2 by n. So x2 is 1 plus 2 by n. 1 plus 2 by n means actually it is 1 plus 1 by n, means it is x1 plus 1 by n, which is nothing but that is equal to 1 plus 2 by n. Similarly, we have x3 will be equal to the x2 plus 1 by n, but x2 is 1 plus 2 by n, so 1 plus 2 by n plus 1 by n will be the 1 plus 3 by n. And continuing in this manner, we have the xn. We have xn means the last end point, that is equal to 2, which will be actually 1 plus n by n. 1 plus n by n means 1 plus 1, that is equal to 2. Okay. So therefore we have xi is equal to the 1 plus I by n, where I varies from 1 to n, and we will choose ti equal to xi. By the definition we know that ti can be any point in the ith subinterval. Here we choose ti equal to xi. Ti equal to xi means the right end point of particular subinterval we are choosing at xi, which means that t1 equal to x1, t2 equal to x2, t3 equal to x3, and so on up to the tn equal to xn. In such manner we are choosing the point ti from the subinterval delta xi. Then we will get, then we have f of ti is equal to f of xi. As we are taking ti equal to xi, therefore f of ti is equal to f of xi, which is equal to the f of, put the value of xi. Xi is 1 plus I by n. So we have f of 1 plus I by n, which is equal to, now use the definition of the function f. F was defined as f of x was equal to 3x plus 1. So in that definition, replace x by this quantity 1 plus I by n. So we'll get therefore f of 1 plus I by n will be equal to the 3 times 1 plus I by n and plus 1. Now simplify this one. 3 into 1 is the 3, 3 plus 1 is the 4, so 4 plus 3 into I by n is the 3I by n. So therefore we have obtained f of ti is equal to the 4 plus 3I by n. Okay, so it is this f of ti. Now we will compute the Riemann sum. Next, we have by definition Riemann sum is SPF, which is equal to the summation over I equal to 1 to n f of ti into delta xi. Now put the values of delta xi as well as f of ti here. So which is equal to the summation over I equal to 1 to n, and f of ti we have just computed, it was the 4 plus 3I by n. So summation over I equal to 1 to n of 4 plus 3I by n into delta xi is 1 by n. Now simplify this one. Okay, Now this is equal to, so this can be written as, multiply this one and perform the simplification. So we'll get this is equal to, I am writing this intermediate step here. Okay, so this is equal to summation over I equal to 1 to n. Then we'll get 4 into 1 by n will be the 4 by n. Okay, 4 into 1 by n is the 4 by n. Then plus, next term is 3i by n into 1 by n is the 3. Okay, it is the 3i by n square. 3i by n square, like such we will get. Next, now as 4 by n is independent of I, okay, as 4 by n is independent of I, therefore we can put this 4 by n outside the summation. Okay, and we will obtain, after putting that 4 by n outside the summation, we will obtain equal to the 4 by n into summation over I equal to 1 to n 1 plus, again 3 by n square is independent of summation I, therefore it can be put outside the summation, and we'll get the second term as plus 3 by n square into summation over I equal to 1 to n of I. So this will be equal to the 4 by n as it is, and summation over I equal to 1 to n is simply 1 plus 1 plus 1 n times, which will be obviously equal to the n. 1 plus 1 plus 1 n times is n. Next term is plus 3 by n square as it is into 3 by n square into summation over I equal to 1 to n of I, means 1 plus 2 plus 3 plus 4 plus up to the n. So we know that 1 plus 2 plus 3 plus 4 plus up to n is the sum of the first n natural numbers, and from the sequences and series we know that this summation is equal to the n into n plus 1 divided by 2. This is its summation. Okay, so n into n plus 1 divided by 2. Now we'll simplify this further. So this will be equal to, so again, so for simplification, this in the first term 1 n, this n will get cancelled from the numerator and denominator. So n will get cancelled with this n, and in the second term 1 n will get cancelled with this n, and the second n will cancel out with this n plus 1, means from this n plus 1 we will take the n common, and that with this n will cancel out this n. Okay, and then whatever we will get, that I am going to write down here. So therefore this is equal to, this will be equal to the, obviously first term is simply 4. Okay, so first term is 4, then plus the second term is now 3 by 2. Okay, second term is simply now 3 by 2 into what is remaining. So from the n plus 1 we have taken n common, and that n is cancelled with the n of the denominator. So remaining is simply 1 plus 1 by n. So 3 by 2 into, it is 1 plus 1 by n. So this much is the remaining, and this is our Riemann sum. Okay, now we will take the limit of this Riemann sum as norm of the partition tends to 0, means as n tends to infinity. So as told just now, the simplification has been made, and therefore what we got here, so it is, see here what we got just now, we have obtained 4 plus 3 by 2 into 1 plus 1 by n, okay, which can be further written as, this can be written as, this is equal to, after multiplying with the 3 by 2, the simplification can be made here itself. So it is 4 plus 3 by 2 if we multiply with the 3 by 2, and plus 3 by 2 into 1 by n is 3 by 2 into 1 by n. Okay, which is nothing but, that is equal to, but 3 by 2 plus 4 is nothing but 8 plus 3 means 11 by 2. So the first term is simply 11 by 2. Summation of the first two terms is the 11 by 2, and second is plus 3 by 2 into 1 by n, or can be written as 3 by 2n also. Now it will be simple to take the limit as n tends to infinity. So we have obtained this as 11 by 2 plus 11 by 2 plus 3 by 2 into 1 by n. Now we will take its limit as n tends to infinity. So therefore limit of this Riemann sum as norm of the partition tends to 0 is same as limit as n tends to infinity of norm of the partition is this much, which we obtained just now. Okay, so limit of this quantity as n tends to infinity. But obviously limit of a fixed quantity or a constant quantity is as it is unchanged. So therefore we obtain this as the limit of 11 by 2 as n tends to infinity is simply 11 by 2 as it is. Okay, and plus then the next term is what? So this is 11 by 2, first term as it is, its element is 11 by 2, plus the next term is 3 by 2 into limit as n tends to infinity of 1 by n, which is equal to 11 by 2 as it is, in then plus 3 by 2 into limit of 1 by n as n tends to infinity is obviously 0. So into 0. Okay, and 0 into 3 by 2 is obviously 0. So we have obtained this is equal to, so this is equal to simply 11 by 2. Okay, now as the limit of the Riemann sum as norm of the partition tends to 0 exists, so which means that the function f is integrable on the closed interval 1 to 2. This is by the second definition of integrability. And the limit we have obtained as the 11 by 2, which means that integration 1 to 2 f dx is equal to the limit of this Riemann sum as norm of the partition tends to 0, and it is equal to 11 by 2. So like such we have solved this first example. Now we will move to the second example. Second example is compute integration minus 1 to 1 f dx, where f of x equal to the mod x. Next one, we know the definition of the absolute value function. The definition of the absolute value function is f of x is equal to the, which we denote by the mod x. Okay, f of x we denote by the mod x. So it is equal to x whenever x is greater than equal to 0, and it is equal to minus x whenever x is less than equal to 0. So obviously this function f is bounded on the closed interval minus 1 to 1, as the interval is finite, therefore it is bounded here. Next, we observe that the function f has different definition to the left and right side of origin. Okay, to the left and right side of origin, function f has different definition. Therefore we have to consider the partition of P. Okay, therefore we have to consider the partition of P in such a way that we have to consider in first part as minus 1 to 0 partition points, in the second part partition points which lies between 0 to 1. So let us consider the partition of closed interval minus 1 as it is considered in this particular case. So P is equal to, it is the set having points x0 which is equal to minus 1, comma x1, comma x2, and continued up to the xn which is equal to 0. It is equal to y0, comma y1, comma y2, comma continued up to yn which is equal to 1. Now where xi and yi are equidistant points, then we observe that from minus 1 to 0 there are n subintervals, and from 0 to 1 there are n subintervals. So therefore we have equidistant points. Okay, so therefore delta xi is equal to delta yi, and which is equal to the obviously 1 by n, because each subinterval is of the length 1 by n as it was in the last example. Next, let xi equal to the minus 1 plus I by n, as we have taken in the last example also. Here also we will take xi equal to the a plus I by n. A means here minus 1, so minus 1 plus I by n, and we will take yi equal to the 0 plus I by n. 0 plus I by n means simply I by n, and here I varies from 1 to n, and we will choose ti as point from the delta xi and ti dash as any point from the delta xi, and let us choose the ti and ti dash in such a way that they are the right end point of the corresponding subinterval. So let Ti equal to Xi and Ti dash is equal to Yi. Then we'll compute the f of Ti and f of Ti dash. So therefore f of Ti is equal to f of Xi, which is equal to the f of, put the value of Xi. We know that f of Xi is equal to the minus 1 plus I by n. Okay, as we have taken the Xi is equal to minus 1 plus I by n, minus 1 plus I by n, and which is equal to the, now f is the absolute value function. So therefore this is equal to the modulus of minus 1 plus I by n. Okay, modulus of minus 1 plus I by n, and this is equal to the 1 minus I by n, because here x is less than equal to 0, therefore mod of x is equal to minus x. So therefore mod of this quantity, as this quantity is negative, therefore modulus of this quantity is the negative of this quantity, and negative of this quantity will be the minus of minus 1 plus I by n, which will be equal to minus of minus plus 1, and minus into plus will get minus I by n. So this is f of Ti. Next, and f of Ti dash is equal to the f of Yi, which is equal to the f of, put the value of Yi. Yi we have considered as the I by n. So f of Yi means f of I by n, and as I by n is a positive quantity, therefore f of I by n, which is simply as the mod of I by n, which is equal to I by n, as y is, as here yi are the positive quantities. Next one, therefore we have, now here we have divided the Riemann sum into two parts for our convenience. Therefore Riemann sum over partition P for the function f is equal to, it will be equal to the summation of, it is equal to the sum of the two summations, which is equal to the summation over I equal to 1 to n f of Ti into delta Xi plus summation over I equal to 1 to n f of Ti dash into delta Yi. Now put the values of f of Ti dash, delta Xi and delta Yi. Then we will obtain, this is equal to summation over I equal to 1 to n, f of Ti was 1 minus I by n, so we have substituted its value, into delta Xi was 1 by n, so we have substituted its value, then plus summation over I equal to 1 to n, f of Yi was I by n, so therefore I by n, into delta Yi means again 1 by n, so which is equal to, as this 1 by n is independent of this summation I, so therefore it can be kept outside the summation. Okay, so but before that we will multiply both the terms by the 1 by n. So first term will become summation over I equal to 1 to n, 1 by n is kept outside, so we will get 1 by n into summation over I equal to 1 to n of 1. Then second term is summation over I equal to 1 to n minus of I by n square. So from that 1 by n square we have kept outside the summation. So therefore the second term is minus 1 by n square into summation over I equal to 1 to n I, plus, now next term is 1 by I by n into 1 by n is the 1 by n square. So the next term is plus 1 by n square summation over I equal to 1 to n I. Okay, if you observe here, then the second term and third term is exactly same, so they will get cancelled. Okay, and therefore what is left here? So left is only, we have left with only one term, that is the first term here. Okay, here the second term and third term are exactly same with opposite signs, therefore they are cancelled. So therefore we have obtained, this is equal to, so this is equal to 1 by n into summation over I equal to 1 to n of 1, which is equal to 1 plus 1 plus 1 up to the n times, and 1 plus 1 plus 1 n times is simply n, and 1 by n into n, again n will cancel from the numerator and denominator, and we have left with only one quantity, and it is 1 itself. Okay, so now as this Riemann sum is a constant quantity, and Riemann sum is a constant quantity, what does it means? Therefore it's a limit, as norm of the partition tends to 0 is constant. Okay, so therefore we obtain limit of the Riemann sum as norm of the partition tends to 0 is equal to limit, put the value of Riemann sum which was 1, as norm of the partition tends to 0, then the n tends to infinity, and limit of 1 is 1 as it is a constant quantity. And as the limit of the Riemann sum as norm of the partition tends to 0 exists, therefore, by definition we can say that the given function is integrable on the closed interval -1 to 1. Okay, therefore the given function is integrable on the closed interval -1 to 1, and its integration is the nothing but limit of that Riemann sum which I obtained just now, and hence we have integration -1 to 1 mod x dx is equal to the limit as n tends to infinity of SPF, which is equal to 1. So like such we have solved this example also. After solving this example, we will move to the next article, which is about the applications. So in that we are going to study 3 applications and 1 corollary based on it. So first application is, application number 1 is if functions f, f1 and f2, where f is equal to f1 plus minus f2 are bounded and integrable on the closed interval a to b, then integration a to b f dx is equal to the integration a to b f1 dx plus or minus integration a to b f2 dx. This is the first application. And if you remember, we have already proved this result in the unit number first, theorem number 5 and 6. In the theorem number 5, we have proved for the f1 plus f2, and number 6 we have proved for the f1 minus f2. Okay, this is the combination of those two theorems. There is one corollary on this first application, and that corollary is if f1 belongs to R means f1 is a Riemann integrable and f2 is also Riemann integrable over closed interval a to b, and c1 comma c2 are any two constants, then we have c1 f1 plus c2 f2 is also Riemann integrable over closed interval a to b, and in this case we have integration a to b c1 f1 plus c2 f2 dx is equal to the c1 integration a to b f1 dx plus c2 integration a to b f2 dx. So this is a corollary, okay, which follows from the application first. Now after this first application and a corollary based on it, the next one is the application number second, and the second application is if a function f is bounded and integrable on each of the intervals closed interval a to c, closed interval c to b and closed interval a to b, where c is a point in the closed interval a to b, then we have integration a to b f dx is equal to the integration a to c f dx plus integration c to b f dx. And if you remember, we have already proved this as the result in the unit number first as the theorem number 7. So in the theorem number 7 we have proved this result already. Now next one is the application number third. So third application is a function f is integrable over closed interval a to b if and only if for every epsilon greater than 0 there exists a delta greater than 0 such that if p and p dash are any two partitions of closed interval a to b with their mesh less than delta, then we should have the difference of Riemann sum over the partition p for the function f and Riemann sum over the partition p dash of the function f should be less than epsilon. Okay, if this difference of Riemann sums over partition p and p dash is less than epsilon, then the function is integrable, and if the function is integrable, then this difference is less than epsilon. So like such is the application number third. So in the today's class we have studied the definition of Riemann sum, we have solved some examples on Riemann sum, we have also studied the second definition of integrability, and at the end we have studied 3 applications on the definition of Riemann sum. So today we'll stop here and we'll continue in the next class. Thank you.